Hi folks, now we're on I guess this is part 4, where we're going to talk about Doppler shift. Now, this is continuing in our discussion about the interaction of light and matter. And so Doppler shift is something that we are familiar with in everyday sort of fashion. And let me pause here and let me show you some pictures associated with, just to remind you about what these things are. I'm going to use sound waves and water waves as an example of light Doppler shifting. They are not entirely exactly the same, but I want to give you an idea that other waves, we can use other waves as a way of understanding Doppler shift. Okay, so that's what we're going to do now. Okay, so hopefully this is working. Notice the change in pitch. High pitch, low pitch. And it won't matter if you're traveling or you're stationary on the Earth. Now we can also show this using a ripple tank. And the ripple tank will allow us to see it with water waves.
The wave moving out from a stationary source travels equally in all directions. Notice how the wave fronts appear to pile up in front of the moving source and seem to spread out on the back side of the source. For a source moving much, much slower than the waves in front of the source are only slightly more compact than those behind the source.
The wavelength is shorter on the right side than on the left side.
On the front side of the moving source, the waves are closer together. On the back side of the moving source, they are farther apart. The speed of the source is about 3/4 of the speed of the wave. Notice how the waves are beginning to stack up on the front side of the source.
Okay, let's go back to our charts. So we've seen how Doppler shift works for sound waves and for water waves. The same thing applies to light waves. The actual physics and how the change in frequency or change in wavelength is slightly different. But the overall effect is the same. So by the time I'm going to talk, this thing is going to play itself out a few times, and we'll see it a few times as well. Notice the yellow and the white star are emitting the same frequency light. That's the characteristic that we're showing over here. And you're viewing, here the observer, you're looking back this way. So A is this guy, and the blue side of the spectrum is here, the red is here. So as it's moving towards you, and then we're moving away from you. Okay, so it's becoming, the blue is more over here, I hate this thing. Um, when the star is here, it's slowing down. You know, this is the most energetic it's going to be, and then it's going to become less energetic, and then over here it's going to become less energetic still, and then from here on it's going to get more energetic. So from here to here it's faster, here to here it's slower. Okay, and when the stars are right across from each other, they will line up because they are moving crossways relative to you. So look for when A and B are here, then the frequency that we should see is right down the middle. And when they are, okay, so here they go, right down the middle. And then when they're here, when they're here and here, they're going to be the most energetic and the least energetic. Now we can apply that to galaxies too. So this is for guys that are close by to us, okay, called spectroscopic binaries. Now for galaxies, you probably heard that all the galaxies are moving away from us. You know, they're lactose intolerant. And what we can see from their spectrum, if we take a spectrum of their stars and compare that to the sun, then we see that all of their frequency absorption bands, all the absorption bands here, are pushed to the right, or pushed to the top, which is more towards the red part of the spectrum, which means that they're moving away. Hence the idea of the expansion of the universe. Okay, so the next step is to talk about radioactivity. Radioactivity comes in 3 bits, alpha, beta, and gamma. As you can see here, alpha particles are the heaviest things. They're basically helium nuclei. Beta particles are electrons, and gamma rays, we've talked about those before. Now, the ancients, from 1850, if we can call those ancients, did all sorts of fun and games. Not only did they burn elements to see what kind of lights they could create from them, which, by the way, is how we, make firecrackers and fireworks shows of different coloring. We use elements like that to give us the colors. But they also discovered things like uranium and radium and pitchblende, which is where that's from, the element that they were using. And they would try to figure out what these things were. Lots of interesting history. But the idea I want to get across here is, suppose you have a source of particles that are coming out, these radioactive particles. You have a radium source, say it's uranium, and you surround it in a lead brick such that you don't get irradiated and get cancer. Okay, well then you put a magnet around here, and what you'll find is you can bend some of these particles one way or the other way, and some of them you can't bend at all. Now, all these particles are roughly carry the same energy. Okay, it's a transition in the nucleus. We've been so far talking about transitions in the atom. This is a different energy regime. Okay, we're talking about transitions in the atom itself, in the nucleus of the atom. Okay, a lot more energy there, roughly 1,000 times more. Alpha particles have a lot of mass, and so when I'm changing the energy of an atom, some of the energy goes into the creation of the mass. So these guys move slowly. On the other hand, photons, or gamma rays, have no mass at all. So they're going to be the most quick. Well, naturally, they're going at the speed of light. And you know that there is a speed limit. Nothing can go faster than the speed of light. But the electrons here that are getting produced also travel very quickly. Okay, we can see that in this picture here about which are the most penetrating. And penetration has to do a lot with how fast these things are going. And you can see that the alpha particle, being so massive, doesn't get through much. I mean, just a sheet of paper would stop it. Electrons, on the other hand, you would need a sheet of aluminum. Granted, aluminum is not very thick, but if you try to punch your hand through it, it won't work. You could shoot a BB and maybe get it through, certainly a pistol or something. But a gamma ray goes through bricks of lead like a hot knife through butter. right? I mean, it just goes right through it. Now, the other interesting thing about radioactivity is that it allowed us to figure out what atoms were made out of. I don't think I've talked about this before, but the original theory about atoms was not one that you currently have in your mind, namely a nucleus, a hard rock center nucleus with a bunch of electrons floating around outside. The original idea behind a nucleus was basically, well, not a nucleus, but an atom is analogous to, say, a blueberry muffin. People at that time, we're talking about the 1850s, 1870s, people knew that electrons were particles, that they were, like BBs, and, you could shoot them at stuff, and they would hit stuff, and, they would bounce off, and they would cause other things to move around, like my example of you getting hit by by a surfboard or something in the ocean, as opposed to being moved around by the wave. So think about a blueberry muffin as the original idea. So they knew about electrons. The blueberries in the muffin would be analogous to the electrons in the atom. The floury portion of the muffin, the paste, if you will, or the bread portion of the muffin, that would be the positive charges, spread over the atom. Okay, and if you shot radioactive particles, a beam of radioactive particles at a bunch of atoms, and this is very, very thin foil, like 3 atomic layers. You can do that with gold foil. If you shot this beam of radioactive alpha particles at this thin foil, then if you had a blueberry muffin, then all the particles would go sailing through. Very rare, it would be, you would never, in fact, see what was observed is that sometimes when you do this experiment, what was observed was totally different than what they expected. What they observed was sometimes these particles would hit the gold foil and come back. Now let me talk about a little bit about the energy involved here. Imagine that you go down to the Iowa in San Pedro Harbor, and you shoot off one of those 16-inch guns. And then you hang a piece of tissue paper in front of the weapon. What would your expectation be? Well, your expectation ought to be that the shell is going to go right through the tissue paper. And that was the expectation that people had for this experiment here. That as they shot these particles through with lots and lots of energy, that they would just go sailing through this thing as if it wasn't there. Just like the Iowa shell going through a piece of tissue paper. Imagine their surprise when some of these things came back at them. Could you imagine shooting a 16-inch shell at a piece of tissue paper and having it bounce back and coming back right at you? I find that really surprising. But that's the analogy that those people had back in the early 20th century. Amazing people, those guys. And we're standing on their shoulders. All right, now why does this matter? Well, we have 2 other forces to consider here, and that's where the radioactivity comes into play. We have, after all, in these nuclei, we have positive charges. And the only way that we can account for the fact that they are still stuck together, right? I mean, after all, positive charges repel, is that we have these neutrons in there. And remember, hydrogen is the only element where I have the possibility of 1 proton, or I only have protons in the nucleus. Every other atom, every other element has certain numbers of neutrons. And as I get bigger and bigger, in the number of protons, then I need many more neutrons to give me the glue necessary to hold these things together. Now, the nuclear force is very, very short range. So in this particular case, I'm overdoing the power of the neutrons. And over here, I'm not getting enough power to hold the nucleus together. That's why nuclei with lots and lots of protons are typically radioactive. And that's why nuclei with small numbers of protons are not radioactive. And in fact, I can create bigger atoms. Now, it turns out that I'm overdoing the nuclear force here of attractiveness, and over here I'm underdoing it. So there is a point in between these two where I'm in the perfect regime, where it's just enough and not too much and not too little. Okay, and that becomes very important when we're talking about stellar evolution and how stars evolve through their lifetimes. All right, a neutron, as in this picture, it will decay. I think it decays in about 5 minutes. It will convert into a proton and an electron, and this is one of the radioactive occurrences we see with atoms. So here we have a picture here where a proton is formed from a neutron and an electron gets ejected. We also have the possibility where a nucleus just gets rid of a whole bunch of stuff. So 2 protons and 2 neutrons. Now, I can't answer the question is, why do I only see alpha particles being emitted rather than saying the nuclei of, say, lithium or the nuclei of oxygen or something like that? I can't answer that. But just let it be said that the only 3 types of radiation I've got are alpha particles, are beta particles, and then it can have gamma rays coming off of a nucleus. Now, the other way that we describe radioactivity is through the term called half-life. Now, a half-life is characterized by how long it takes for half of the material to decay from the parent to a daughter. Okay, so in this particular case, we're looking at uranium. Uranium is the parent, and lead is the daughter element. So I have a kilogram here of uranium, and then I look back 4.5 billion years later, and half of it's gone. Okay, then I look another 4.5 billion years, and half of that which was left has now converted into lead. And then I look after, in the same sample, another 4.5 billion years, another half-life, and half of that which was left, the 1/4 of a kilogram here that was left, half of this amount has been converted to lead. It isn't the case where here I go, half of it is gone, right? And then the next time, the rest of it is gone, or the next half is gone. No, it's half of that which is left. Half of that which is left. Okay? And that allows me to figure out how old something is relative to other processes. Now, half-lives associated with any particular element are not that simple. Okay? There's all sorts of, there's a particular path, and the path can be rather meandering. So here I have uranium. I go down to, whatever this guy is, thorium, and then I come back up to uranium. But notice I have changed how many nucleons I have going from here to here. And then I go back to thorium again, and then radium, and then I'm just continuing on. Here's an interesting situation. I can go either this way or I can go down. And then over here, I can come this way to get to bismuth. I can come over here this way, and then I can either go this way or I can go that way. Anyway, I'm going to end up at lead. Okay, now this is the case for uranium-238 coming down to the lead-82. All right, now here is a chart where, it's a more complete chart, if you will, of an isotope table. Now we can do this. I've shown you natural ways of doing this, from going from uranium down to lead, but I can do this artificially as well. So in this particular picture, I'm bombarding nitrogen, regular common nitrogen that's in the atmosphere, for example, with a helium nucleus, with an alpha particle. And when I do that, I create oxygen, and then I create a proton. As I said, I can do this by human means. Now, this is sort of related to, say, carbon-14 dating. And the idea here is cosmic rays will produce neutrons. The neutron hits a common element of our atmosphere, nitrogen, and it will convert that into carbon-14, which is radioactive, and it will create a proton to boot. Now, at some later stage, the carbon-14 will convert back to nitrogen and will emit an electron. Okay? Now, the idea is this. There's a certain amount of carbon-14 being created, and it's in equilibrium in the atmosphere. Plants absorb this carbon-14 along with carbon-12 and a little bit of carbon-13 that's out there. But basically, we're comparing the amount of carbon-14 to carbon-12. If the plant is in equilibrium with the atmosphere, then the amount of carbon-14 compared to carbon-12 should be at the same ratio in the plant as well as in the atmosphere. When the plant is no longer in equilibrium with the atmosphere, then the carbon-14 will decay. The plant no longer is in equilibrium with the atmosphere when it dies. Now, the same idea applies to those things that are in equilibrium with the plant, namely animals that eat the plants and animals that eat the animals which eat the plants, of which we are part. So an easy way to figure out how old something is, if it's organic, is to figure out what is the ratio of carbon-14 to carbon-12 in the material. So take a piece of an old log and burn the elements and see how much carbon-14 you have to carbon-12. If you have radioactivity, if it's no longer in equilibrium, then the amount of carbon-14 that is in that material is no longer there, right? So you're going to have less amount of carbon-14 to carbon-12. All right, so I could, let me say QED, that gives you the numbers of half-lives, and then if you know what the half-life is for carbon-14, multiply one number by the other, and you got the age of the element, the age of the item you were trying to date. Now, carbon-14 is not the only one that is radioactive that we use to date things radioactively. There's a whole plethora of elements that we can utilize. One is uranium. And in fact, in my room that I can show my face-to-face students, is I have a rock that I picked up on the Angeles Crest Highway, and it is supposedly 1.7 billion years old. I think it is amazing to be able to hold something in your hand that is almost as old as the Earth. Now, the way people know that these rocks are that old is that there is uranium in these rocks, and they are absorbed in a thing called a zircon crystal. Zircons preferentially like uranium to hold on to, and they don't like lead. So if I count up the number of lead elements in there, because after all, it's in a crystalline structure, and if the uranium changes its characteristic, it can't get pushed out, even though it's now lead rather than uranium. So it's still stuck in this crystalline structure, but it's no longer held together with molecular bonds to any other element. But it's still there. So you can go wandering around in this rock and count up uranium atoms versus lead atoms. And do the same thing that we just did with carbon-14, or that picture that I showed you of uranium converting into lead. So I know that these rocks are 1.7 billion years old. It took me a little effort to find these things, but my biggest thing was to try to figure out if this rock was a Mendenhall gneiss. And I talked to some geology friends of mine, and they said it was. and Mendenhall gneiss in the Angeles crest is 1.7 billion years old from dating of zircon crystals. So, pretty interesting little sidelight there. All right, now the next step is to show you some videos here. I'm going to show you this video. It's on my, well, as you can see, it's on my hard drive here. And what I'm going to do is instead of showing it on my hard drive here, I'm going to link it to the next installment. Now, there's a couple here which are from the Creation Liberty folks. These people are, I believe, young Earth creationists, and this person here is very much against young Earth creationists, and it's kind of fun to listen to. He has some good points in it. These guys, I don't think they have a leg to stand on, and if you remember our section talking about creative thinking, and especially in terms of fallacious arguments, you'll hear a number of them here. You'll hear a few of them here as well. There's lots of straw man being put up, but it's sort of a clever way of putting forth the information. Okay? Thank you.